So first of all, definition of a parametric equation is if we have two functions that are continuous on a specific interval I, and we pull their ordered pairs from those two functions, what we're going to end up with is a plane curve C, and that is the equation x equals f of t and y equals g of t are the parametric equations for C, because t is a parameter. In other words, what we're doing is we're finding we have two variables for a position and one variable for time, and we're combining the two. Okay, that kind of makes sense? Maybe not? Okay, have you seen something like this in physics class? Okay, so chances are you will, eventually see something like this in a physics type of class. So what happens is, if we're sketching a plane curve and we have f of x is t squared minus 4 and g of x is t over 2, we're going to use the same numbers for t, plug them in to figure out what the x and the y's are for those. And then we're going to plot just the x and the y's. So that's why this is a bluer color. Those will eventually be plotted, and we'll be able to see our parametric curve. Okay, so I gave you kind of a starting point, and I said, hey, let's let t be -2, -1, 0, 1, 2, and 3. So when we plug in -2 everywhere we see t, we'll have a -2 squared minus 4, and -2 squared minus 4 is 0. So when we plug -2 in for t, we get 0 for x. Now we'll plug -1 in. So -1 squared minus 4 is going to get us, and 0 squared minus 4 is going to get us, and then when we plug in 1 squared minus 4, we get -3 again, and when we plug in 2 squared minus 4, we're going to get, and when we plug in 3 squared minus 4, we'll get. So those are going to be the x values that we eventually plot. Now we do the same thing with y, and in this case we're going to plug in these same numbers into t over 2. So a -2 over 2 is going to get us, and -1 over 2 is going to get -1/2, and 0 over 2 is 0, and 1 over 2, +1/2, and 2 over 2, and 3 over 2. 3/2 or 1.5, depending on how you want to think about it. Okay? So now that we've done that work, all we're going to do is plug in or plot those points. So we're plotting the x and the y. And this was defined for the interval -2 to 3, so we tried all the integer values. We could have also put in non-integer values, fractions, decimals, and so forth, but we like to start with our integers. So t can be -2. That means x can be 0 and y can be -1. So we want to put a point at 0 over 1 down. Another point at -3, -1/2. A third point at -4, 0. And then a point at -3, +1/2. And a point at 0, 1. And a point at 5, 1.5. Okay. So then we connect the dots in the order in which we plotted them. So we start with our -1, because it can be a -1 that's solid, and we're going to draw this curve, and we're going to stop at the point 5, 1.5, and not put an arrow here. But what we do is we indicate the direction in which this curve was going by putting a couple of arrows on the graph itself. And that just shows you the motion. Okay? So what questions do you have about this slide? All right. So the next one says that we're going to sketch the plane curve where x is the square root of t and y is t plus 2, provided that t is greater than or equal to 0. So we're only going to use 0 and positive numbers. And they could be fractions. They don't have to be integers, but we can plug in various things. So let's think about some good numbers that we might want to try. 0 is an obvious one because that's the start of our interval. I like the idea of 4, 9, and maybe 16 might get too big at 16, right? So maybe a 1. We better probably throw a 1 in here, and if you want to erase, you can, or you can put the 1 below. All right, so we've got some good numbers to try. So now we plug these into our x is equal to the square root of t and find out that we get 0, 1, 2, and 3, right? I guess I could show you, or show the steps. You don't have to once you get the hang of this. But we did this by design, right, to come up with some nice numbers. Okay, now we're going to plug in numbers like 0, 1, bless you, 4, and 9 again, right? But this time, when we plug these in, we're going to have a 0 plus 2, a 1 plus 2, a 4 plus 2, and a 9 plus 2. So we'll have 2, 3, 6, and 11. So far, so good? All right, so because t could be equal to 0, that means that 0 is in our domain. And so we'll plot 0, 2, close circle there because of the equal to. And then we have 1, 3. And we have 2, 6. And finally, we have 3, 11. So our parametric curve is starting out here at 0, 2 and moving in this direction. Can it keep going? Yes. So we can put an arrow on the end of this one saying, hey, this is the direction it's going, and it gets to continue on because my interval was not restricted on the max side of things. Questions on this one? Okay. So now we want to switch gears a little bit and say, hey, what happens if we want to make this into an equation that doesn't deal with t's, x's, and y's, is only working with x's and y's? So we want to put it in the rectangular coordinate system. So you solve one of your equations for t, and then you substitute it into the other one, and you simplify. That's the easiest way to make that happen. So if we have x equals t squared minus 4, and y equals t over 2, ask yourself which one is probably the easiest one to solve for t. The y, right? Because it's only it has a t divided by 2, so if we solve this for t, t becomes 2y. Okay? So now that we have one of the equations solved for y, we'll substitute that t back in, or solve for t. We substitute the t back in to get an equation with just x's and y's. So we'll have x equals 2y squared minus 4. Okay? And let's simplify that a little bit. X would be 4y squared minus 4. Right? And we're used to having that solved for y, aren't we? So when we plug in numbers for x, we get nice, neat numbers for y. So if we're solving this for y, we'd have an x plus 4 over 4 is equal to our y squared, right? Or if you want to think of it as x plus 4, well, and that would be basically 1/4 x plus 1 is y squared. And then y would be the square root of that. So basically we know we have a parabola, right? Which way is it opening? If it's y squared, it's going to open to the right. Okay, so we've got a parabola opening to the right. Okay, so now let's think about what values we can plug in for x. So we're trying to figure out if y is equal to the square root of 1/4 x plus 1, what would be some good numbers to plug in that are going to come out nicely? 4 would be 1/4 times 4. Let's start with 0. 0 is always good to start with, right? Okay, when we plug in 0, we're going to get the square root of 1, which is 1. But is it positive 1 or negative 1? Plus minus, because we needed to introduce when we took our square root. Okay? What's another good number? 16 would get us 4 plus 1, which is the square root of 5. And we can use a decimal, but I like 12 better. Why do I like 12 better? Or not 12, but yeah, 12 is better. Okay? Because when we plug in 12 for x, 1/4 times 12 is 3. 3 plus 1 is 4. Square root of 4 is, okay? So that's still kind of messy. What about a negative number? What would be a good negative number to put in there? Negative, not negative 12, because we're still going to end up with way too big. We want to get in, we would like to get negative 16 would get us a negative 4 plus 1, but what about negative 20 isn't going to be so big, right? Okay. What about a negative 4? Is negative 4 going to fit in our graph? Because negative 4 times a fourth is a negative 1. Negative 1 plus 1 is 0, right? Square root of 0 is 0. Okay? So let's work with these guys since we are kind of restricted on our graph paper here that I gave you. So we'll be at 0 and plus or minus 1. And then we will be at negative 4, 0. Okay? So far so good? Does that even make sense when you think about it? Why would this be negative 4, 0 for a vertex? X was 4 times y, let's see, y squared minus 1, right? So can you see where we're going to end up by completing the square where we will get our vertex at negative 4, 1, or negative 4, 0? Okay, so as it's coming this way, it's going to go like so, right? And go like so. All right, so questions on this one? Okay, so, good question. And basically, we were just converting this guy to a rectangular form, and there were no restrictions on it, so no, not so much. Okay, so when we're asking you to write the arrows on it is when we're actually asking you to graph the parametric form. Okay, far so good? All right. So here is our last one of these, and then we have one that is going to look a little bit polar. Okay, so now we have x equals 1 over the square root of t plus 1. And we have y equals t over t plus 1. Which one's going to be easier to solve for? The y, because how are we going to get a t all by itself? We have t in two places. So that's going to be harder to get the t all by itself, isn't it? But what happens if we try to solve for t here? Because the square root's a little scary at first, right? Yes, we're going to have an x squared. So what we can do is two different ways. You can either cross multiply and to take that t plus 1 to the top, right? Or you can say, hey, I'm going to end up having to square things eventually anyway, right? So as long as I square both sides, we're legal. So we have x squared equals 1 over t plus 1. So far, so good. And if you want to think about that as inverting both sides, you can. Or if you want to think about that as cross-multiplying, you can. We'll have an x squared times this t plus 1 is equal to 1, right? And we're trying to get the t plus 1 all by itself, so we would divide by x squared. So if t plus 1 is 1 over x squared, what do we have to do to get the t by itself? Subtract 1. So t will be 1 over x squared minus 1. So we have solved one equation for our t. And now we have to do what with it? Plug it into the other, substitute it in. Okay? So when we substitute this in, y will be equal to 1 over x squared minus 1 over 1 over x squared minus 1 plus 1. Let's do this again. 1 over x squared minus 1 plus 1. Okay. And the denominator, what's that going to simplify to? Over x squared. So we have 1 over x squared minus 1 over 1 over x squared. Now why can't we just cancel the 1 over x squareds with each other? Because of that negative 1. They're a difference, not factors. When they're factors, we can cancel, but when we have sums and differences, we can't. So what are we going to do? We want to kind of get rid of this denominator, right? So what can we multiply by to make that denominator go? We put an x squared over 1, that makes that disappear, right? But as long as if we're doing that to the denominator, we have to do the same thing to the numerator. Okay, simplifying these crazy fractions. All right, so y is now going to be equal to 1 when we take the x squared times 1 over x squared, and a minus x squared, and this guy all disappears. So that's not so bad. Okay. And then we could, if we were asked to, we could graph it. So that's a parabola opening down and to the left. X squared. So it's either going up or down, right? Because it's x squared. And so we're going to go down. Okay? And we could complete the square and simplify and all that fun stuff, or find our 4p and so on. Okay, so last example. Kind of looks like a rose curve, right? Unless we don't have an r. Now we have an x and a y. So we're going to combine a rose curve with a rose curve sans the r's. All right, so let's think about what we're doing here. Okay, before we had to solve for t, right? So here it looks like we would need to solve for what? For theta, okay? But let's think about what happens if we solve this for theta, okay? If we would solve this for theta, we would have to divide by 3 and then take the inverse cosine, wouldn't we? Okay, so the inverse cosine of x over 3 would get plugged into here, and the sine of the inverse cosine of x over 3 times 4, is that going to help us? No. So we had to take a different tactic when we're dealing with thetas. So I have a feeling that we may want to use a trig identity here. So what was our favorite trig identity because it was the easiest one to remember? Sine over cosine is tangent, right? But we don't necessarily want to get y over x. We want to do something to simplify things. But which other one dealt with sine and cosine? Cosine squared plus sine squared equals 1. Or I think we in our book we had it written as sine squared plus cosine squared. Okay, so if we're going to use that, we would need to substitute some things in, right? So y here is going to be equal to the sine of theta as long as we divide it by 4. How would we get the sine of theta by itself? So we can square it and substitute it in. That makes sense? And the cosine of theta would be x over 3. So far, so good. So now we have a y over 4 that we can square. And an x over 3 that we can square. And that should be equal to 1. See how we've eliminated our theta, and now we just have x's and y's? Okay. Now we're used to writing our x squared first, right? So x squared over 9 plus y squared over 16 equals 1. What is that the equation of? An ellipse. Centered at what? At 0, 0 at the origin. Has a major axis that is the x or y axis. Nope, just reminding you. Okay, so the y-axis is the major axis. So we know that it is opening, it's figured left and right. It's a horizontal, sorry, vertical ellipse. And then what? So from 0, 0, our vertices are at 4 and negative 4. 0, 4, 0, negative 4. Okay, and our endpoints of our minor axis are 3, 0, and negative 3, 0. And then we would go ahead and draw our ellipse. So you may have to do some creative things when you see things with thetas, right? All right. Questions on this one? Okay. Assignments. Bless you. Odds are in the back of the book, so make sure you're being honest and doing your job. Only using that to check.